Okay, great. We are now at the last stretch of our discussion for MEADMAT. And now we will talk about numerical solutions for uh, for differential equations, right? So last time we were hooking you guys, I was hooking you guys with this whole divide between analytical and numerical, right? So for the first part of this course, we were talking about analytical methods, right? Basically, a recap on differential equations and how we can solve systems of multiple equations with analytical, basically brain power methods. Now we will talk about the brute force methods, right? And admittedly, you might say, okay, why don't we just use analytical methods? Number one, well, not every differential equation has an analytical solution. Based on the techniques we've found so far, right, we can only get a handful of differential equations. And even then, right, some of those equations might be a little bit too much for us. Like analytically, right, there are there are different topics out there relating to what the Bessel function, those kinds of things, and I suppose they're more related to what electronics or electrical engineers do, maybe. Right? We may be in that purview, but for now, I will choose not to steer us in that direction, and instead, I will introduce numerical methods. Right now, we have three. We have Euler's method, improved Euler's method, and the Runge-Kutta method or the RK4 method. I will discuss all three of these, but you will see they're just going to be parang steps in difficulty, right? They will get a little bit more complicated every single time, and then we will compare them with the solution, with the analytical solution for our example, right? So we will start with the most simple. We have Euler's method, and you guys can understand hopefully how this will work. Right? You will have in here a function, right? You will have here a function, a differential equation, and of course this will only work for first order differential equations. You have here only a first derivative of y with regards to or with respect to x, right? And you will then isolate that value of y prime, or basically that dy over dx, and then leave everything else afterwards. That will be your function. Okay? And then you're going to get your initial values. The thing is, you cannot use numerical methods to solve for for general solutions, right? That is a completely different beast, right? And what you're going to do is you're going to get what we call a step value called h, right? This is either, right, a time step. Usually this x variable here is of time, right? And so usually this is what we call a time step, but this is going to be a small step in the direction of the independent variable, usually nga time, right? And then you will immediately have your next iteration. Your next values are going to be this. You might say, okay, how does this work? Okay, what we're going to do in here is that we're just going to graph a very simple kind of a coordinate axis right here. And the goal is not for us to be able to solve this just using a graph, but to just show everybody in here, right, how this is supposed to go. If this is the analytical solution, right, what we're going to do basically is that we're going to try and find out a numerical approximation, right? Because we don't know, say for example, what what do you call this? What the shape of the analytical solution is going to be. We're going to guess, basically, right? What we're going to do is do something like this. Say for example, this is our initial value of x0 and y0. x0, y0. What we're going to do in here is that we're going to elect, say for example, a time step, right? A time step. Maybe it would be better if I put it here just for spacing purposes. There you go. x0, y0. Okay? And what we're going to do in here is that we're going to elect what we call a time step, right? This h value. Say, for example, this h value is this large, right? Say, for example, this h value is this large. Okay? So that means that this thing, right, that this x coordinate is now going to be xo plus h. Makes sense, right? That's going to be where our new x coordinate will land. And notice, if you keep doing this, you will just add steps of h, so on, so forth. What will happen here? Now, for the y coordinate, what you will do is that you will add to your original y coordinate h times that function. You might notice, okay, well, what does this mean? Right? H times whatever this derivative is. And you might say, okay, why does the derivative matter? It's because you are basically trying here the rise over run of the function, right? The rise over run of the function. Note that in this case, your run, because you have decided to move forward in the direction of x, right? By a distance of h, right? This is going to be h now, right? What will happen in here is that this run is now decidedly h. And so you will now get the rise, the appropriate rise. Now, what does that look like in here? Currently, this equation, right? This equation or this analytical solution, we don't know the shape of it, but we know at the very least that because of the differential equation, we get to know the slope of it. How do we get to know the slope? This is because this dy over dx is the slope of your function. So say, for example, we know the slope of this function is going to be like this, right? And if you scale it such that this horizontal direction right here is h, that means that this is going to be h times your rise over run, which is going to be h times your dy over dx. And so now your next point will be, right, your next point will be here. And notice that is very close to wherever the original function is. So that kind of closeness is why Euler's method works, right? It's going to be close because you're looking at the tangent line of the actual function. It's just that you don't know the shape of the function, right? If we continue this, what will happen is that now we know, because of the differential equation itself, we are going to know the slope of this function at this point. It's going to point like this, and it's going to point like this. But because we are not in that situation, right? Because we are not in that situation, this will now go like this, right? And so you will now accrue, you will now accrue more and more error. We're going to look at the original points. And if you're going to continue, right, you will continue accruing more and more error. Sometimes the error gets corrected, sometimes it blows out of proportion. So what we're supposed to do is that we're supposed to employ a really small, as small as we can get, a small value of h. The smaller the better, but of course the thing about a smaller step size is that you're going to step really small values, or you're going to take really small steps, right? So that means you're going to take a long time for you to render the image of the equation, right? So that's what happens, right? The thing about this now is that you might say, oh, okay, that makes sense. The problem with Euler's method is that trade-off, right? So you might want to, you might say, okay, is there a better way that doesn't have to make me pick a really small step size? Maybe, right? What we're going to do in here now is that we're going to improve Euler's method. You might say, oh, what is this, right? What's basically happening in here is that now for the improved Euler's method, let's draw this again. What we're now going to do is that we're going to take the average. Average of what? Right? Say, for example, we're going to have our function again. We're going to have our initial value again, right? In here. Say, for example, our h is now going to be a little bit larger, just to show you guys what's going to happen, right? Originally, this h is going to be right here, and say, for example, this tangent line is going to look like something like this, right? So it's going to end up in here, right? This is where the Euler method would have taken us. So this is your h times your dy over dx, or let's just say h times f of x0 and y0. Now we will take that result, right? We will take that result and temper it. What do you mean temper it? As in, what we're going to do now is that we're going to take this value, right? Say, for example, we know now that the slope is going to be like this. I don't know. I can't Maybe this is good. Let's transfer it down here, right? We'll see that this is another h. Maybe that's not, it's not long enough. But the thing about this now is that you will now have this other proportion. You will now have another h in here, another h in here, and then another hf. But now this is of the next iteration, x1, y1. The thing now that's going to happen is for you to get somewhat of a better result, because notice, right, that that error, or rather that true value, is going to be, in this case, is going to be a little bit above your value or your original value. What you're going to do with the improved Euler method is that you're going to take this value and copy it in here. Now you have two different values, one that is orange and one that is yellow, and now you're going to be able to temper it by taking the average of these two slopes. Notice that they now bound that red point. And so that means that your calculation is going to be much more accurate, shall we say, right? So in this case, you do not need such a big, such a small value of h for this to have a better result. This is what entails Euler's improved Euler's method. And so as you may see, right, this y result is not very appealing to the eyes, right? So what we usually do is that we now include values of k, right? If you have k1 and k2 right here, which is hopefully easy enough to follow for you guys, right? What you will have is a smaller version of y1. Notice that for the Euler's method, say for example for Euler's method, what should I use? Maybe Euler's method is red. For Euler's method, your next iteration of y will be yo plus what do you call this? H times f of xo yo, right? And then in the improved Euler's method, what you will have in here is y1 equal to yo plus, I feel like we should take this one down like that. There you go. And then we divide this by 2. We now get the average of, right, k1 and k2. Right? In this case, k1 and k2 reference different values, different slope values. Whereas this one, if you want, can just be labeled as hk1. Right? And then we will take this even a step further with the RK method, the Runge-Kutta method. Instead of having just 2 iterations as compared to 1 for Euler's method, as compared to 2 for the improved Euler's method, you will get 4. And we will take this notion of the average and make it a little bit more complicated, or rather a little bit more refined, by basically doing half steps. Look at this, h over 2, right? What you are now doing for this is that you are now trying to understand, okay, we want this to be as truthful, or rather as accurate as possible, without sacrificing the need for smaller and smaller values of h. What we will do is then, okay, let me try to draw this. This is going to be a little bit of a more difficult task of drawing. So I suppose we only need one value of h then. We're going to only have one value of h. Might as well have it really large. Okay, so that is our original point. Say for example, this is our value of h, this really long thing right here. So that means our value of h over 2 is going to be half of this, which is going to be 2 grid lines instead of 4, right? What you will notice is that this first one right here will simulate this, well, what do you call this? Will simulate this. You know what? Let's make this a little bit more clear. There you go. We will simulate this first slope, right? We'll simulate this first slope, which is f x0 y0. Okay, so we will simulate this slope like this. Okay, maybe you should pick another color. Yeah, blue will work. Let's look at this one here. That will be your k1. Okay, now your k2 is you're going to have to advance by half a step. Note that this is not a full step, this is just half a step. Okay, and now what will happen is that you will use the information in k1 to feed it into k2. So it's saying, where are you currently in here? You are looking at this point right here, right? So let's color that with blue. And then what will happen is that we will pass on this point right here, or rather the slope of this point right here. What is the slope of this point right here? Be this. Go. And then let's pass it down here. Right? And then let's pass it down here. So now we are getting two pieces of information. As you can see, right? We are seeing that it's a little bit higher than our supposed value, right? Which is here. And then let's continue and let's continue. Wait lang, let's remove this. Right? Let's continue with that information from K2, right? Let's feed it into K3. Right? Let's feed it into K3. We will again move half a step. Right? Notice that we are now here, right? But then again, we will have a different, another, right? Another kind of what do you call this? Another kind of slope, right? Another kind of slope. Say for example, we are now here. Let's have this passed on like this. Maybe I think it's like this, a little bit higher. Okay, and let's pass it down here. Okay, so now we're getting somewhat different pieces of information. You know, let's exaggerate this just for the sake of just for the sake of illustration. Right? And then finally we gain a full step, right? We gain a full step. We use this information from K3. We go to the full step now. Right? We're going to go to K4, which now feeds all of the information we know. You know what? Yeah, let's just keep going. I think I've done this a little bit out of scale, but we'll keep going forward. Okay. So now what we'll do is we'll get the tangent line. Okay. Pass that on. There you go. Okay, so apparently these two have somewhat of the same slope. Let's just make that a little bit more exaggerated. And so now these four pieces of information that you have are going to dictate where your step is next going to be, right? And so you might say, oh my gosh, there's a lot of stuff that we need to do for RKN. Well, we'll find out how accurate it really is supposed to be if we do a little example, just one example for any kind of differential equation. This is just for first order. Our last topic will be for second order differential equations. You guys probably know what that is already. But what we'll do this time around is that we will have number one, the analytical solution displayed. Number 2, 3, and 4, we will have Euler's method, improved Euler's method, and the Runge-Kutta method. As you can see in here, if we're going to illustrate this point, the RK4 method is going to have, well, y1 is equal to y0 plus, what is this, h over 6 now. H over 6, you will have k1, and then 2, k2. Note that what they're doing, right, in this case, is that they are weighting more the middle portions, right? They are not weighting as in like weight, giving weight. Right? Allocating weight na lang is a better way to say it. Right? They are allocating higher weights for the ones in the middle. Very interesting. Right? So these are the differences between the three equations that we have. Right? Oh, sorry, the three methods, pala rather, the three algorithms. And the thing is, with these algorithms, if you know how to do it, right? If you know how to do it, you should be set, right? As in, if you're going to do this in Excel, you just drag it down and you're going to be fine. Okay, so we will have this example, dy over dx is equal to x plus 3y, where y of 0 is equal to 0.1. What we'll have in here is a first order differential equation. If you want, you can find out that this is going to be a linear differential equation. You guys can solve it like that, but right, with what we've learned, you can also do this using method of undetermined coefficients. You might say like, well, this is not a second order differential equation. I agree, but you can do this all the same. How? Well, what we're going to do is first we're going to find out what the analytical solution is going to be, right? We will just express this as y prime, and then you'll say is equal to x plus 3y. And notice that now I can do y prime minus 3y is equal to x. What we can do now is express this in terms of the differential operator. You'll have dy minus 3y is equal to x. And now you see, oh, I see. The thing is, this is non-homogeneous because there is still a value on the right-hand side, right? So what we will do is we will consider that first to be 0 and deal with the x later on. Now what we will have is d minus 3 times y is equal to 0. You can very clearly see that the answer here is d is equal to 3, which means our general solution is going to have an a e raised to 3x. However, this is not yet done because we still have the value of x in here. And so our guess, right, based on the method of undetermined coefficients, if x is your right-hand side, that means that that is an algebraic or a polynomial kind of guess. What we're going to have here is the complementary solution, which should also be in the form of a polynomial, right? And the highest, excuse me, excuse me, the highest power in here is 1, so we should account for that. Bx raised to 1, and then we should account for all of the lower powers afterwards, which is now plus c. Now we can put everything together. You will have your general solution in here, which is going to be ae 3x plus bx plus c. The thing about this is that the a is the only real arbitrary constant, right? This is the thing that you're supposed to solve when everything is done, when you're going to have your particular solution. That means that you have to determine these undetermined coefficients b and c. How do we do that? Well, we're supposed to put them in the original equation. So if you're going to, right, put this and derive it with respect to x, you will get 3a e 3x and then plus b. Now we will put everything together into this equation. You will have y prime, which is 3a 3x plus b is equal to, this is going to be x plus 3y, right? So x plus 3y, 3 times a e 3x plus bx plus c. Okay. Now what we will do is that we'll just expand everything. X plus 3a 3x plus 3bx plus c. Okay. And now what we will have in here is cancel this, cancel this. You will now have b is equal to x plus 3bx plus c. And then basically you're going to have to look at all of the ones with an x, right? The ones with an x right here and the ones with a constant right here. And you're going to basically compare them, right? On the other side, there's no x in here, so we'll just say that that is going to be 0x plus b. There you go, right? And so we will see in here that 3b plus 1 is going to be equal to 0, which means that your b in here is going to be equal to negative 1/3. Since your b is equal to c based on the blue markings, right? Based on the blue markings, that means that your c is also going to be negative 1/3. And so that means that your answer in here is going to be, right, y is equal to ae raised to 3x minus 1/3 x minus 1/3. Okay, that's going to be your answer. And now we'll plug in our values of x equals 0 and y equals 0.1. Y equals 0.1. So that we find out our value of a. What we will do now is, well, substitute, right? 0.1 going to be equal to a e raised to 0, right? 3 times 0 is just 0. This is just going to be equal to 1 minus 1/3 times 0 minus 1/3. Okay? And so what will happen now is that you have cancel as well. You'll have 0.1 or 1/10 is equal to a minus 1/3. That means that your a is going to be equal to 13/30. Something like that. Okay, let's just try. Right? 1/10 plus 1/3. You butterfly that, that becomes 3 plus 10, 13/30. Yep, 13/30 is our A. That means that our final answer, our analytical answer here, our analytical equation should be 13/30 e raised to 3x minus 1/3 x minus 1/3. Okay, so this is our analytical solution. That is what we'll be doing in a while, or rather, that is what we'll be comparing with these two values in a while. So let's just see what that looks like in here. So this is going to be 13/30. Then you will have minus x over 3 minus 1/3. What you will have, there you go, is your 0 and 0.1. And what we want to see is this rise right here. Okay, what we want to see is this rise over here. And if we're going to set our boundary, or if we're going to set our endpoint to 8, to x equals 1, our y value should be 8.03707. Okay, so we need to look at that as soon as possible. Or we just need to look at that. Okay, so close this. We will have, or rather, what we will do is set a kind of a universal thing in here. We will have our differential equation. Oh, everything is still in. You know what? I should change. So let's go for Fourier this. Fourier. Okay. Have our differential equation in here. What you will say is that your y prime is equal to, what is your y prime equal to? X plus 3y. X plus 3. Okay. So let's just enter that thing. We'll have our h in here. Let's just say that that is going to be, I don't know, 0.2 or maybe 0.5. We'll see, right? And then we will have our x0 and our y. That will be in here. You will have your 0 and then you will have your 0.1. See how these things will take it. Okay. First, we will have our analytical method, right? Our analytical method. Just have it as Anna here. And what you will have is x. Oh, yeah. X and then y. Let's make this 0.1. Okay. This 0.1. You'll have your 0, your initial value in here. And then your y value, right, is going to be unlocked by this thing. It's 13/30. So what we'll do, 13 divided by 30 times exponent of 3 times this is this value. This is B9 minus 1/3 times B9 minus 1/3. So that's 0.1. And what we will do now in here is that we will add this to your value of h. And what we will do is we're going to lock that value so that we won't let it get that kind of a. Oh, sorry, I was looking at the h itself. Supposed to say C3. There you go. And what this will do now, if you drag it down, is that it will just update your values of, well, x based on your h and not the consequential values afterwards, right? The values after, right? What we will do now is that we will just update it like this, and now we will see that the answer indeed is going to be 8.03707, just like what Desmos says here. Okay, let's actually make this a little bigger. Oh, okay. It stops there. Okay, so that is our real value, right? And so what we will do now is that we will start with our Euler's method. Right? Euler's method. Okay, start with Euler's method. And then, excuse me, what you will have in here is x and then y, and then maybe our f, right? F of x. Those are your values for the Euler's method. And then what we will have here is we will again start with our 0. Okay? And then our y value in here, which is going to be 0.1. That's what we know. Right? Those are the things we know. And what we will do is that we will follow this thing, right? Religiously follow this thing. We will have x, right? X plus 3 times y. Okay? And what will happen now is that your x will continue in this fashion, right? We'll have this plus this value, and then we will lock those values right there. And now do it something like this. And then we will also lock these values, or we will drag these values down, right? And what we will do now for y is that we will update it like this: y plus h, and again we will lock that value so it doesn't move when we try to drag it down, times, right, this value right here. Okay? There you go. So now you will see how it's going to be just a little bit different. It's going to be a little bit different. Okay. All right. So what will happen now is that this value of f will be underrepresented, or rather this value of y is way under what we think, or what they think it's supposed to be. Right? Let's try this now. Let's try and make the the h value a little smaller, 0.05. Right? We'll see that the error is still way far. Right? What about 0.01? Okay? At this point, the value, or rather the error, is still quite far. Okay? Where do we get error, Kai? How will we get error? Maybe the error should be just on top, right? Error here you will have is absolute value of this minus this divided by, the error is about 36%. So that's quite high. Okay? Turn that, let's give it a few more digits. There you go. That's your error for the Euler's method. Let's make it a little bit smaller. Yeah, and of course the error will decrease as you get smaller and smaller values of h. But the thing is, where are you going? Right? This is quite small. This is quite small. If we try to make it a little bit further down, right? If for example we get it to 30 iterations, or let's just end it at there. What you will see is that still the error is quite high. The error is still quite high. Okay. Let's update this. Let's make this 39. Everything is 39. There you go. Still quite a high kind of error. Okay. So now let's see what the IEM, the improved Euler's method, can do. We have x, y, and then we have values of k1 and k2. Okay. And so let us religiously follow what they are telling us to do. Okay. We will have x0 in here. We have y0 in here as well. And then what we will do is now compute this value of k1. This value of k1 is, where is it? Okay. Value of k1 is just the solution of x f of x0 and y0. Basically just the original kind of function, x plus 3 times y. Oh, that is your k1. And then your k2 will now involve basically x. But now instead of x, it's going to be xo plus h. Right? Notice that this is now xo plus h. So what we will do is now, this is now x plus h. This value of h, let's lock that again. And then plus 3 times your value of y plus h. Again, let's lock that. Times the value of k1. Right? So now you see that it incorporates the information that you're supposed to know from k1 into k2. Right? And so your k1 is k9, I think. K9. And once it's all over, what you will do is, well, you will improve this, or you will have this step by, what is that, k C3, right? C3. And then your y value will be, what is this? Your y value will be yo plus h over 2 times k1 and k2. Right? So it's going to be this plus 1/2 times your C3, right? Your H value times this one plus this one. So it's an average, right? So now you see that. And now we will drag these down, right? And then we will basically drag everything down. Let's see how this improves, right? Still not great. Still not great. So the error now for this thing, let's look at this, will be absolute value of this divided by C39. So the error now is going to be 16%. Well, okay. Not that great still, but yeah. Are we doing something wrong? And now that I'm thinking about it, 0.5. Ooh, look at that. The error is 100%. I mean, okay, what we're dealing with here is an exponential equation. So it's gonna be a little bit loopy talaga. So let's make this a little small. 0.1. There you go. So these things are going to, well, they're going to have radically different values. And then let's say, for example, 0.05. So quite high error values still, right? So now let's showcase the famed RK4. Okay, the RK4 is going to be way more complicated. It will have K1, K2, K3, and K4. And well, we should begin, right? Your X will be just the same as this thing, C4. Your Y should be C5. Yep. Your K1 is going to be, well, it's just going to be the original one, X plus 3 times Y. Okay? And then your K2 will be, you will start taking half steps now. Here, you will half step, and then you will half step as well. Okay? What will happen now is that you will have X. Sorry, I really just wrote down X. And then half a step of your step value, C3. And then plus, oops, okay, plus 3 times Y. Our Y value here is 09, I think. Yep, 09 plus 0.5 times the value of our step value. There we go. Times the value of K1, which in this case is P9, I think. Okay, there you go. Is that right? Yeah, K1 over 2. Yep, that is correct. And then we proceed. We will proceed now. We will have this plus 1/2 again of your step value C3. And then plus 3 times your value of Y. Your Y is this thing again, plus 0.5, half a step of your step function, C3, and then times, now we will go with K2. This is now Q9, if I'm not mistaken. There you go. And then finally, K4, you will now take full steps, right? This is now going to be added to just the value of C3. And then what you will have in here is 3 times Y. So this is Y plus H. So this is just C3 times the value of K3. So that is now R9, I think. Yep. We have followed everything here, right? First, we just took the original slope. Next, we took the original slope, but using the information of K1, we put it in here and we took a half step, right? And next, using the information in K2, we got the next iteration right here. And then we took a full step for K4, and now we will weigh all of them together. Now, what we will do is this, you add by your C3, And then this now will be y plus 1/6 times your value of the h, right? And then you will have k1 plus 2 times k2 plus 2 times k3 plus k4. So now that is how we weight it. Then we can drag everything down again, and well, the everything repeats, right? Everything repeats. And so we can drag this down. See what happens. And so perhaps this 52.56, let's try it now here. This minus this over C39. Okay, so 51%. I suppose it's going to be the smallest one out of all of these. Right? But I'm now doubting the authenticity of our answer here. Because, well, everything in here seems to suggest, right, the answer is going to be 18-ish. Why is this 38? Let's make sure. 0.001. The error is going to be 16%. So somehow they're all off. Now I'm starting to kind of doubt our solution in here. X plus 3y. Put it over there. We got our answer, which was AE raised to 3x. Then we got this, which was now. Okay, you know what? I'm going to ask for the advice of Wolfram Alpha. Let's remove this. Wolfram. Yeah. Y prime equal to x plus 3y. Y of 0 is 0.1. Let's see what they say the answer is. The answer is going to be, oh, the y0 is 0.1. Where's the differential equation? Ito. Okay. So 2, 1, 1, 1, 1. And apparently, the y value, or rather the value should be, oh, there it is. There's the mistake. Oh my goodness. Wow. So the differential equations caught it before I did. Very interesting. So this should be 3c instead of c. Now we have this b equals 3c. That means that your c is now going to be 1/9, negative 1/9. So in this case, instead of this being 13 over 30, this should be 19 over 90. Is that right? If we get this to be 9, we can now say that this is 9. Oh, this is 10 over 90. So this is 1/9. Is that right? It should be 110 plus 19. Should be 9 plus, no. It's 19 over 90. 19 over 90. Let's put on these correct values this time. 19 over 90. This should be 1 over 9. Then let's see how it pans out at the bottom. So maybe it didn't set off. Oh, wow. Oh my gosh. Look at that. Okay, so because of systematic error, that's what we call it, right? Because of systematic error, we were able to diagnose that there was something wrong with the analytical solution, which was quite cool. I admit my mistake there, but that is quite cool. Like we were able to get it because of the fact that these things are supposed to work very cleanly, right? Say for example, we now get it to, I don't know, point 0.5. Let's get it to 0.5. You'll see that the values in here, okay, 0.5 is quite large. Try 0.25. Oh wow, look at that. The error for the Euler's method is astronomical, right? It's quite high, it's quite off. But in the RK4 method, it remains at about the same amount, 3.15, right? It got it got the order of magnitude correct, which was very interesting, very interesting. Say for example, even in the point fives, the error of the RK4 is 40%, which is quite large, but still, if we make it 0.1, everybody's everybody's errors is 67%, 10%, but RK4 is at 0.05, just so you guys understand how powerful it is. Of course, at the cost of a lot of computation for one iteration, but still, those iterations pay off very clearly. Right? There you go. That is our analysis, right? And it's a very poignant analysis how even even the analytical solution, we found that to be wrong because of the appearance of a kind of a systematical error where earlier they were all at 16%, 16%, 16, right? Try this out at 0.05, and well, the error here is just like plain zero. Let's try to increase. Yeah, there you go. So that is quite small. The error there is quite small. Oh, so you guys know how powerful RK4 is, of course, at a cost. At a cost. Okay? That is going to be it, right? For our last this for the last part of our discussion for MEADMAT, all in all, we will have the RKN method, right? Which is used basically everywhere else, right? If you have a second order differential equation, that is the way forward. Okay? So that'll be it. Thank you very much.